Welcome back to the deep dive. Now, if you were with us last time, you'll remember we actually ran some quantum code on real hardware.
Right. That was fascinating.
It was. But you probably also noticed, well, the results weren't perfect, were they? We saw those error counts alongside the expected outcomes.
Yeah, those little imperfections are key.
Exactly. And that leads us straight into today's big question. Why are quantum computers, at least the ones we have now, so fragile? It's this imperfect reality, this single biggest hurdle on the way to, truly fault-tolerant machines. We're talking about quantum noise, decoherence, and this massive quest for stability.
Absolutely. And that's our mission today, really. We're diving into taming the quantum chaos.
I like that title.
Understanding these practical limits isn't just theory. It's crucial if you want to get a real handle on where quantum tech is today, and honestly, where all the important research is pushing towards.
Okay, so let's unpack this. We're going to explore, first, the fundamental challenge, this noise and decoherence thing.
Yep.
Then, how do we actually measure how good a qubit is? We'll look at T1 and T2 times.
Key metrics.
Then the really clever stuff, quantum error correction, or QEC. What are the principles behind it? We'll also touch on error thresholds, why they matter for fault-tolerant computing, and then zoom in on the leading strategy there, the surface code.
Right, the front runner for now.
And finally, we'll look at where we are right now, the nisq era, its state, its challenges.
Sound good. Sounds like a plan. Let's get into it.
All right, let's start with the basics. A classical bit in your phone or computer, it's pretty solid, right? It's a transistor, a voltage level, it's either 0 or 1. Generally robust.
Very robust, relatively speaking. It's a macroscopic thing.
Exactly. But a qubit, that's a whole different story.
Oh, completely. What's really interesting here is the contrast. A qubit, whether it's, a trapped ion, a superconducting circuit, whatever, it's a microscopic quantum system. Incredibly delicate. Its state, especially that superposition state, is just extraordinarily fragile. It's constantly being jostled and disturbed by, everything around it.
The environment.
Precisely. And this unwanted interaction, this constant poking from the outside world that randomizes the quantum state. That's what we call quantum noise.
So noise isn't just static on the line, it's actively messing up the computation.
It's the arch nemesis, really. It corrupts the quantum information stored in the qubits, and it disrupts the quantum gates, the operations themselves. Errors just pile up.
And it's not just one thing causing this noise.
No. It's a collection of different culprits. We can sort of group them. First, you've got environmental noise, which is often just called decoherence. That's the big one, the interaction with the surroundings.
Yeah, okay.
Think about thermal fluctuations. Even tiny amounts of heat cause vibrations in the chip material. That's why these superconducting quantum computers need those massive refrigerators.
Right. You mentioned cooling them to near absolute zero, like 15 millikelvin.
Colder than deep space, yeah. Just to minimize those thermal jitters.
Wow. Okay, so heat is one enemy. What else is out there in the environment?
Well, then you have stray electromagnetic fields. These can come from the control wiring itself, the electronics nearby, even cosmic rays zipping through. They can nudge the qubit states.
Cosmic rays? Really?
Oh, yeah. They can pack a punch at that quantum level. And then there are material defects. Tiny imperfections, impurities in the silicon or whatever material the processor is made from can act like little traps or bumps in the road for the quantum state.
Okay, so that's the environment fighting against the qubit staying pure. But what about when we try to control them? Does that cause problems too?
Absolutely. That's the second category. Control noise. These are errors that come from the very act of trying to run the quantum gates.
Like trying to flip a qubit.
Exactly. Take pulse imperfections. We use microwave pulses or lasers to manipulate the qubits to rotate them. But maybe the pulse isn't exactly the right shape or duration or frequency.
So a 90-degree rotation might end up being 89.9 degrees.
Precisely. And that tiny error, it accumulates over many gates. Then there's crosstalk.
I think I can guess this one, like signals bleeding over.
You got it. You try to apply a gate pulse to one specific qubit, but a little bit of that signal leaks and affects its neighbors. It's like trying to whisper a secret to one person, but the person next to them overhears it wrong.
That makes perfect sense. It's a crowded neighborhood on those chips.
It really is.
So with all these noise sources, thermal, EM, material defects, imperfect pulses, crosstalk, what actually happens to the qubit's information, how does it manifest as errors?
Good question. These different noise processes boil down to causing two main kinds of fundamental errors. The first is pretty intuitive. a bit flip error.
Like a classical bit flip, 0 goes to 1 or 1 goes to 0.
Exactly, the quantum analog. A qubit in state 0 might flip to 1 or vice versa. Simple enough.
Okay.
But then there's the second type, which is uniquely quantum, a phase flip error.
Phase flip. Okay, that sounds less intuitive.
It is. Remember, a qubit can be in a superposition, like having both 0 and 1 Urey character at the same time, with a relative phase between them. A phase flip error messes with that relationship.
So like the plus sign on Urey plus 1 becoming a minus sign, 1 Urey.
That's exactly it. It flips the relative phase.
Yeah.
And in reality, a qubit isn't just experiencing pure bit flips or pure phase flips. It's usually some combination, some random drift of its state vector across the Bloch sphere.
It sounds like keeping these things stable is a nightmare. How on earth do researchers even measure how bad the noise is or track if they're making progress?
Right, you need metrics. You need ways to quantify this. And researchers use a few key ones to really benchmark their devices and compare different approaches. It connects to the bigger picture of seeing whose hardware is improving faster.
So let's get into those. You mentioned decoherence earlier, the qubit losing its quantumness. How is that measured?
We mainly use two characteristic times. The first is T1 time, also called the relaxation time.
Relaxation, like relaxing back to the ground state.
Exactly. If you put a qubit into its excited state, one hail, T1, tells you, on average, how long it takes to decay back down to the ground state, 0 Aurea. It's directly related to those bit flip errors. Longer T1 is better, means it holds its energy longer.
Okay, T1 is energy lifetime. What's the other one?
The other is T2 time, the dephasing time. This one is about how long the qubit maintains its phase information. It's quantum memory, you could say. How long can it remember the specific superposition it's in?
And that relates to the phase flip errors.
Directly. T2 measures how quickly the superposition decays. And an important point, T2 is always less than or equal to T1. You can lose phase information much faster than you lose energy.
And which one is more critical?
Arguably, T2 is often considered more critical for computation because superposition is where the quantum magic happens. If your T2 is too short, your computation basically falls apart before it can finish.
But the progress here has been pretty amazing, hasn't it? I remember reading that these times used to be tiny.
Oh, incredible progress. If you look at superconducting qubits, T1 and T2 times have gone from nanoseconds, maybe 20 years ago, up to hundreds of microseconds in the best devices today. That's orders of magnitude improvement.
A huge leap. That must be down to better materials, better fabrication.
Better everything, really. Material science, fabrication techniques, shielding, qubit design. It's a multifaceted effort.
Okay, so T1 and T2 measure how long a qubit can passively survive. But what about when we're actively using it, hitting it with gates?
Right, that's where gate fidelity comes in. This isn't about passive decay. It's about the active quality of the operations. Fidelity asks, how close was the gate I actually performed to the perfect date I intended to perform?
And that's measured as a percentage or a number between 0 and 1?
Yep. 1 or 100% means a perfect gate, 0 errors. And today, the best systems are achieving really high numbers for simple gates. Single qubit gate fidelities can be above 99.9%.
99.9.
And two qubit gates, which are more complex and crucial, like the CNOT gate, are often above 99%.
Okay, now here's where it gets really interesting, right? Because you listening might think 99.9%. 99%, that sounds fantastic.
It sounds great in isolation.
Think about it. 99.9% fidelity means 1 out of every 1,000 single qubit gates goes wrong. And a useful quantum algorithm might need millions, maybe billions of gate operations.
Suddenly, that 0.1% error rate per gate becomes completely catastrophic. The errors just accumulate and overwhelm the calculation. You get garbage out.
And that right there is the core reason we need something more. That's the motivation for quantum error correction.
Precisely. We can't build perfectly noiseless qubits or perform perfectly flawless gates, at least not yet, maybe never. So since you can't eliminate the noise entirely, you have to find a way to manage it, to live with it.
Now, in classical computers, we handle errors with redundancy, right? Like making copies?
Yeah, the simplest classical error correction is just that, redundancy. Want to protect a bit, make 3 copies. If one flips due to some random error, you just take a majority vote of the 3 copies to figure out the original value. Simple and effective.
So the obvious question then is, why can't we just do that with qubits? Just copy the qubit state 3 times.
If only it were that simple. That classical strategy completely breaks down in the quantum world for 2 really fundamental reasons.
Okay, what are they?
First, the no-cloning theorem. This is a fundamental principle of quantum mechanics. It states you absolutely cannot create a perfect independent copy of an unknown arbitrary quantum state. You just can't clone a qubit if you don't already know what state it's in.
Okay, no copying allowed. What's the second reason?
The second is just as critical. Measurement destroys superposition. Remember, to check if a classical bit is flipped, you just measure it. But if you measure a qubit that's in a superposition to check for an error,
you collapse it. You destroy the very superposition you were trying to protect.
Exactly. You kill the quantum information in the process of trying to check it.
So no cloning and no direct checking. That sounds like a serious roadblock. How do we possibly fix errors then?
This is where quantum error correction, QEC, comes in. It's this really brilliant and highly complex set of techniques designed specifically to get around these two quantum roadblocks.
And the core idea is, well, how would you describe it? It seems almost magical, fixing something without looking at it.
It kind of does.
Yeah.
The genius of QEC is that it finds a way to detect and correct errors without learning the underlying quantum state, thus preserving the superposition.
How?
The basic principle is to encode the information of one single ideal qubit, what we call a logical qubit, into the shared collective entangled state of many actual physical qubits.
So spreading the information out.
Exactly. Spreading it out redundantly, but in a very clever quantum way using entanglement. Then, instead of measuring the physical qubits directly, because that would collapse the state, we use other qubits called ancillary or helper qubits.
Okay.
These ancillary qubits interact with groups of the data qubits and measure a kind of collective property, like are the qubits in this group the same or different, or some other parity check. They don't reveal the state of any single data qubit.
They just reveal relationships between them.
Precisely. And the pattern of outcomes from these ancillary measurements gives you what's called an error syndrome. It's like a diagnostic code. This syndrome tells you if an error occurred, what kind of error it likely was, bit flip or phase flip, and where it happened, all without revealing the delicate Aya and make amplitudes of the logical qubit itself.
That's pretty mind-bending. Could you maybe walk us through a simplified example, like that 3-qubit code I've heard about?
Sure. The 3-qubit bit flip code is a great conceptual illustration. Let's say we want to protect one logical qubit. We can encode the logical state 0L as the state where 3 physical qubits are all 0 SOAOA.
Okay.
And the logical state 1RL is encoded as 111. So a general superposition AOL plus 1L becomes the entangled state AOL plus 111 across the 3 physical qubits.
Right. Information spread out. Now, what if an error happens? Say the middle qubit gets flipped by noise.
Good example.
Yeah.
So a bit flip, an X error hits the second qubit. The state Asinodis plus 01 array becomes A0J plus 101 array. Now, we don't measure 0, 1, or 0 directly.
Right. No peaking.
Instead, we use ancillary qubits to measure the parity. Basically, are they the same or different between qubit 0 and qubit 1, and then between qubit 1 and qubit 2.
Okay. What would those checks tell us in this case?
Well, comparing qubit 0 and away and qubit 1 away in the first part of the superposition, they're different. Same for the second part, 1 away, 0 away. So the first parity check says different. Then we compare qubit 1, went 1er, and qubit 2, 0 away in the first part, different. And qubit 1, 0 away, and qubit 2, 1 away in the second part, also different. So the second parity check also says different.
So the syndrome is different.
Exactly. And this specific syndrome, different, uniquely tells us that the error must have been a bit flip on the middle qubit 1. No other single bit flip error gives that result.
So the syndrome pinpoints the error location.
Precisely. And once we know a bit flip happened on qubit 1, we could just apply a corrective X gate to that qubit, flipping it back and restoring the original encoded state Asinora plus low 111.
Without ever knowing I or a ball.
Without ever knowing I or a ball. And similar codes exist to detect phase flips, and more complex codes handle both simultaneously. The core idea is encoding non-locally and measuring syndromes.
That's a really neat illustration, but obviously real quantum computers will need something much more robust than a simple 3-qubit code. What's the leading approach for actually building a large-scale fault-tolerant machine?
Yeah, the simple codes are great for understanding, but for practicality, the front-runner right now is the surface code.
The surface code, I've heard that mentioned a lot. What is it?
It's a type of topological QEC code. The topology part refers to its structure. The physical qubits are arranged on a 2D grid, like a checkerboard.
Okay, a grid of qubits.
And on this grid, you have 2 types of qubits. You have data qubits, which sit at certain locations and collectively store the encoded logical qubit information. And then interspersed between them, you have measure qubits or ancillary qubits. Their only job is to repeatedly perform those parity checks on their neighboring data qubits to look for errors.
So the measure qubits are constantly poking their neighbors, in a sense.
Constantly checking up on them, yeah. And there are two flavors of these measure qubits corresponding to the two types of errors we worry about.
Let me guess, one for bit flips, one for phase flips.
Exactly. There are Z measure qubits that check for bit flip, X errors, on the data qubits around them. And there are X measure qubits that check for phase flip, Z errors, on their neighbors.
So how does the error detection actually work on this grid? What does a syndrome look like?
Imagine these measure qubits are constantly performing their checks. Let's say a Z measure qubit checks 4 neighbors. Normally, if there are no errors, it should measure, say, +1. But if a bit flip error happens on one of its data qubit neighbors between checks...
the next time it checks, the result will be different.
Precisely. The outcome flips, maybe 2 mega 1. It's like that measure qubit raises a flag saying, something changed here. Now, a single error might flip the outcome of 2 adjacent measure qubits.
Okay.
And if errors keep happening, you get a chain of these flipped measurement outcomes, these flags, creating a kind of path across the surface of the code.
Path representing the errors.
Essentially, yes. And the really cool part is that there's a sophisticated classical computer algorithm running alongside the quantum processor. Its job is to look at this pattern of syndrome flags appearing over time.
A path.
And decode it. It has to figure out the most likely sequence of actual physical qubit errors, git flips and phase flips, that would have caused that specific syndrome path to appear. Then it knows what corrections to apply.
Wow, so there's a whole classical decoding process happening in real time.
A critical one.
Yeah.
And one of the main reasons the surface code is so popular is what we call its high error threshold.
Okay, you mentioned thresholds earlier. Tell us about the error threshold theorem and why the surface code's threshold is such a big deal.
Right. The error threshold theorem is maybe one of the most important results in quantum computing theory. It's incredibly optimistic, actually.
How so?
It basically says this. If the error rate of your physical components, your qubits and gates, measured by things like gate fidelity, is below a certain critical value called the threshold,
okay,
then you can, in principle, make the error rate of your logical qubit arbitrarily small, essentially perfect, just by adding more physical qubits and making your error correction code bigger.
So as long as your hardware is good enough below the threshold, you can eventually achieve fault tolerance.
That's the promise. Errors can be actively suppressed faster than they accumulate. Now, this raises the crucial question. What is that threshold value? Different QEC codes have different thresholds.
And the surface codes is good.
It's considered very good, relatively speaking. The theoretical estimates put it around 1% physical error rate.
1%? That still sounds quite high, error-wise.
It is, compared to classical computing. But for quantum systems, achieving physical error rates below 1%, like the 99% or 99.9% fidelities we discussed, is within reach, or already happening for some gates. A code that can tolerate errors up to 1% is much more practical to build than one needing, say, 0.01% error rates.
I see. So its high threshold makes it the most realistic path forward with current or near-term hardware.
Exactly. That's why it's the leading candidate. But there's a trade-off, a big one.
Which is?
The overhead. To get one really well-protected, near-perfect logical qubit using the surface code, especially if your physical error rate is close to that threshold, you might need thousands, maybe even tens of thousands of physical qubits.
Thousands of physical qubits for one logical qubit. Wow.
Yeah. The resource requirements are enormous. That's why building a truly fault-tolerant quantum computer is such a monumental long-term engineering challenge.
Which brings us neatly to where we are today, because we don't have machines with millions of physical qubits to run large surface codes yet.
No, definitely not. That's the long-term dream. Where we are now is firmly in the IceQ era.
In IceQ, that's the term coined by physicist John Preskill.
That's right, back in 2018. It stands for Noisy Intermediate Scale Quantum, and it perfectly captures the state of current and near-future devices.
Let's break that down. Noisy seems pretty clear after our discussion.
Yep, noisy means exactly what we've been talking about. Operations are imperfect, gates have errors, qubits lose their quantum state, decohere, relatively quickly. This fundamentally limits the depth of the quantum circuits we can run, basically. How many steps we can perform before noise just swamps the useful signal.
Okay, noisy. What about intermediate scale? What does that imply?
Intermediate scale refers to the number of qubits. These machines have, say, dozens to maybe a few hundred qubits, perhaps pushing towards a few thousand in the next few years.
So not the millions needed for full fault tolerance.
Nowhere near. Not enough qubits to implement sophisticated error correction like the surface code effectively, but it's also too many qubits to easily simulate their behavior using even the biggest classical supercomputers.
Ah, so they're in this interesting middle ground. Too noisy for complex algorithms, but too big to simulate classically.
Exactly. That's the nisq sweet spot, or maybe the nisq challenge.
So what does this actually mean for you, the listener, right now? What can these nisq machines do? What's the main focus for researchers in this era?
Well, the central challenge of the nisq era is precisely this. How do you find useful applications for these powerful but imperfect machines? How can we get valuable results despite the noise?
So it's about working with the noise, not just waiting for it to go away.
Absolutely. It's an era of real algorithmic ingenuity. People are developing quantum-aware or noise-resilient algorithms, trying to design computations that are naturally more robust to the kinds of errors these machines produce.
What are some examples of areas where nisq machines might show promise?
Several key areas. One is quantum simulation. Using one controllable quantum system, the quantum computer, to simulate the behavior of another quantum system, maybe a complex molecule or a novel material. This seems like a very natural fit.
Simulating quantum with quantum.
Exactly. Another big one is quantum chemistry, calculating the properties of molecules, reaction rates, things that are incredibly hard for classical computers. Even approximate answers from a nisq device could be really valuable for drug discovery or material science.
Okay.
And also optimization problems, finding the best solution out of many possibilities. Here, people are exploring hybrid quantum classical algorithms.
Hybrid, like using both quantum and classical computers together.
Precisely. A good example is the variational quantum eigensolver, or VQE. The quantum computer prepares and measures a state based on some parameters, and a classical computer optimizes those parameters to find the lowest energy state, which often corresponds to the solution. It cleverly uses the quantum processor for the part it's good at and the classical one for the rest.
So it's really about finding clever ways to use these noisy machines for specific, valuable tasks while we continue the long march towards fault tolerance.
That's the nisq era in a nutshell.
Yeah.
It's about practical progress in the face of imperfection.
It really does sound like this whole field is defined by that constant battle against quantum noise.
It truly is the defining engineering challenge.
So let's try and wrap this up. This deep dive, we've seen that behind the sort of clean logic of a quantum algorithm, there's this messy, chaotic, fragile physical reality. Every single quantum computation is fundamentally a race against time, a race against decoherence.
Quantified by those T1 and T2 times.
Exactly. And the unavoidable imperfections in controlling these systems, measured by gate fidelity, just add more errors into the mix.
Yep.
Our current machines, these nisq devices, are impressive feats of engineering, but they're fundamentally limited by this noise. We're exploring ways to get value from them now.
Through clever algorithms and hybrid approaches.
Right. But the long-term vision, the path to truly scalable, reliable quantum computing that could, change the world, that lies through the incredible ingenuity of quantum error correction.
Using strategies like the surface code.
To detect and fix errors without destroying the quantum data itself, using thousands of physical qubits to protect just one logical one.
It's a huge undertaking. And I guess a final thought for you to consider is that this journey from the noisy present of NEQ to the error-corrected future. It really is a marathon, not a sprint.
Decades, maybe?
Possibly. But it feels like the necessary path, the one we have to take if we want to unlock the full, truly world-changing potential of this quantum age.
A challenging but exciting road ahead. Well, thank you for joining us on this deep dive into quantum chaos and the incredible quest for stability. We hope you feel a bit clearer on the hurdles and the brilliance involved in quantum computing today.
Hope it was useful.
And if you enjoyed this exploration, please do subscribe to our channel, Tech AI and Beyond, for more deep dives into the complex and fascinating technology shaping our future. Thanks for listening.